Hello, my name is Eric Weisstein. I work at Wolfram Research. I'm going to be speaking today on the 2019 SI system of units, which redefined units used by most countries in the world and implications that this had for the unit and quantity systems in Mathematica and Wolfram Alpha.
Thank you all for coming this afternoon. My name is Eric Weisstein. I've been at Wolfram for more than 20 years and worked on a number of different projects. Today, I have the honor and privilege of talking about one that came out of one of the pieces of work I do on Wolfram Alpha, which is the unit system. And there was something very interesting and fundamental that happened in the world of units earlier this year, but most people didn't notice. So it turns out if you use Mathematica, you might have noticed because we accommodated these fundamental changes. And today, I want to try to explain a little bit about what happened, why it's interesting, why it's important, and just assure you that Mathematica, as the best way to compute anything as precisely and correctly as possible, is now completely up to date with the correct way to measure units used by all countries in the world except a few minor exceptions that need not be mentioned, like ours. So anyway, on May 20th of this year, there were 4 base units in the SI system of units that were redefined. And they were redefined by basically setting 4 fundamental constants from physics to exact values. Previously, they had been measured when expressed in terms of SI units. The change was they were defined in terms of these physical constants. And this means that in addition to 3 of the 7, which had definitions, the speed of light was exact, a couple other I'll show you later, that means all SI units are now defined in terms of physical constants of nature that are universal, don't change over time, and can be measured in any lab, not on some bar sitting in a vault in Paris somewhere. So one of the goals of the changes was not to make any difference to people who use units. So the new values that were chosen are indistinguishable for all practical purposes from the old ones. So you think, okay, then why does it matter? Well, it matters because the Wolfram language and Wolfram Alpha treat things exactly. And we need to know, is something an exact number? Is it an approximate? Same thing for physical constants. So I'll discuss a little bit in detail about what those things all mean. So before we get to units, I want to talk a little bit about physical constants, since this is now how units are defined. And in fact, US units are now defined in terms of these physical constants now, because US units are defined in terms of SI units. So it actually effectively redefined the US units a little bit too, but again, to an imperceptible amount. So as of version 12, we added a new entity domain, knowing that this SI thing was coming, because it had been under discussion for many years. So we have a physical constant entity domain in which we attempt to curate and collect. And these things were even nicely documented starting. Some of these entities existed before. This is a new one. But all of these, if you haven't seen these entity pages before, now have nicely detailed pages. So if you know about entities but were afraid to ask or didn't know how to use them, look them up in the help browser, and you'll find all sorts of details and useful information about them. So we added this physical constant domain. And as of right now, we have about 287 physical constants in it. Here's an example of some of them that probably too small to see, but they include cosmological things. They include your old friend, speed of light, Planck's constant. And they have various properties associated with them. So let's just take, for an example, the gravitational constant, which it turns out is one of the least well-known. So if you ask for the physical constant entity corresponding to the gravitational constant, we give you the value. That value has, in this case, you can see it's coming back. There's a backtick here. I don't know if you in the back can see, but it's a precision tag number. So this represents the best experimental uncertainty of this number. And this is one that was not redefined exactly in terms of SI units. OK, so if I ask for the precision, there we go. It's known to about 4.3 digits. I can do things like try to ask about the uncertainty in different forms. We have this beautiful new around construct. So it will say it's this number plus or minus this number. And you can also get it back in other forms, such as an interval, precision, whatever. OK, so with most physical constants, the accuracy or the precision they can be measured with increases over time. And it's useful for some people, for some applications, to actually be able to keep track of, what was the best known value of this 10 years ago or 12 years ago. Because some of the international bodies actually define things in terms of the best value was measured 10 years ago. So it turns out that the physical constant domain defines not only the best value today, but you can see here we have code data from 2010, code data from 2006. So we have a historical record of the best values that these constants are known to. Maybe not going back to the beginning of time, but as far as I've gotten back to curating them yet. And you can do nice things like you can plot them. Here I'm just creating a table of, I'm pulling out the values for the gravitational constant, and you can see that one has big error bars on it. That one's still hard to measure. So that would not be a good one to base your definition of the SI system on, because we really don't know it very well. But it turns out and just saying a little bit more about physical constants, where do the best values come from? Well, they're domain-specific standards body, like the International Astronomical Unit. They're geodesy bodies that define, defining ellipses of the Earth. There's Planck collaboration has a good collection of cosmology-related constants from the Planck satellite. The particle data people, have their own best measured values. People publish papers where they measure ones, but one of the best, most widely used, and most standard one is called code data. And that is a group of people established back in 1966 who has a special task force to comb through the literature and basically find the best values, figure out their correlations, and publish standard values that you should use when you use these in calculations. So for instance, I can search for electron mass here. And this is updated every 4 years. And these are all the constants. I know you can't read them. There's the electron mass. And here's the value that it says it thinks you should use. So every 4 years, we have to update physical constant to do that, to include those new values. OK, so where do unit definitions come from for all the world except the USA, Myanmar, and Liberia? They come from the SI system of units, which in turn is overseen by an international committee with a French acronym, because the French are the ones who started this whole process back in 1875. And they have a special committee that meets on a regular basis to make recommendations related to unit measurements. And they make recommendations on a periodic basis, and then they release this thing called the SI brochure, which is the gold standard that says how SI units are defined, how it's allowed to use them, their definitions, and all those sorts of things. So this thing is published sort of at irregular intervals. The last major one was in 2006. This one, the new one in May, came out in 2019. So it's been 13 years since they really changed anything. So this is kind of a big deal in the world of units. And the other good thing about it is since this change, they're not going to have to change too much again, because now these values are set in stone in terms of fundamental things, which has been a goal of metrology for a long, long time. So on May 20th, the 9th edition of the SI brochure was released. As I said, it's the first revision in 13 years. And it completes a process that was begun a half century ago when they started moving away from the lengths of rods and the masses of cylinders to measuring the speed of light, originally defined in terms of vibrations of some krypton spectral line. But then through a series of refinements, they changed it to a definition in terms of, they defined the second exactly in terms of an atomic constant related to vibrations of a different atom. And then they defined the speed of light as an exact number of meters per second when you define the second in this way. So they already had, OK. But until this year, the kilogram was the only thing that remained as a physical prototype. So there's some kilogram in Paris somewhere, and all the units are defined, not all the units, but the kilograms and ones defined by the kilograms depend on that particular man-made arbitrary object. So finally, that is retired. That can move to a museum somewhere. They can show it to people. They don't have to keep it in a noble gas archive and only show it on special occasions. And the SI, as I said at the beginning, became wholly derivable from natural phenomena, which is very desirable. And as I also already mentioned, the new values were chosen so that for all practical purposes, people who measure stuff in labs or use units won't actually notice that they did, which most of you probably didn't. So prior to 2019, there were 3 of the 7 sort of fundamental SI units. The speed of light defined meters per second. Vibration of cesium defined basically the second through hertz, inverse seconds. There's another one called luminous efficacity that was defined in terms of monochromatic emission of monochromatic radiation. Now, in 2009, we covered the other 4 all at once. And the way they were covered is the Planck constant is exactly this number. This is no longer a measured number with some uncertainty. The Planck constant H is exactly that many joule seconds. Yes, sir?
Is it like the luminous efficacy K7CD? It has to be defined as. It's not going to be a round number, right? I mean, it's unlikely that there would be anything with exactly 638 lumens per watt.
That's the thing. It's chosen to define the combination of lumens and watts. So it defines the candela. So it just happens, it's a nice exact number. The second is a nice exact number. And the speed of light, they're all integers. In order to retain compatibility with the existing definitions based on the kilogram, and you can see these others are not exact integers. In fact, so we have Planck constant, elementary charge, Boltzmann constant, and Avogadro constant. When expressed in SI units, these are now exact quantities. So that means if you measure this in your lab, what actually changes is not the value in SI units, but the value of the SI unit itself. So the values of these constants expressed in SI units are set in stone. So one side effect this has, people may have heard of base units. So kilogram, meter, second are considered base units. There isn't really a base, you don't need a base unit in SI anymore because they're all expressible through combinations of these physical constants. But they're kept around because people are used to them and they really are the ones that we encounter most often in daily life. As I said, 7 of them now define the system, they're exact. One curious side effect is though, because of the interrelations between, there are many physical constants and some are kind of related to others in various ways. For those of you who do any sort of electromagnetic or physics, you'll know permittivity of free space or electric constant, impedance of free space. Those used to be exact. There were these things like 4 pi times 10 to the minus 7 or whatever. After this change, defining other constants to be exact, these are now inexact. So it's kind of counterintuitive, but it follows from the whole sort of interconnected network of how things are physically. And in fact, the uncertainties of most physical constants are best expressed and computed in terms of the other physical constants that you can measure best in the lab, which turn out to be the fine structure constant, which you can measure to many, many, many digits, and the Rydberg constant, which is a spectroscopic thing that people have been measuring for hundreds of years, and you can also get to many digits.
So you didn't have the speed of light? It's not one of the 4?
Speed of light is one of the 3 that was already defined prior to 2019. So there were 3, now there's all 7. And I think this will become clear on some of my, okay, so what did this mean for the Wolfram language? Well, obviously for physical constants, which is all I've really talked about so far, we had to add these new definitions, keep the old ones, but add the new ones, and adjust all the values and uncertainties because like Faraday's constant is Avogadro's number times the electric charge. So that now has an exact value when expressed in SI units. So we have to go through and basically update every single physical constant when expressed in terms of SI units, more or less. And Wolfram alpha, it had a few consequences as well. The most immediate was, I don't know if you can see this. So this is probably what you'd expect to see for Planck's constant, 6.626 times 10 to the 34 plus some other digits. But the point is, it's not just some other digits now. It's now an exact rational number. So my colleague Bjorn had to go through and make some adjustments in order to make sure that we can show you the exact value, but we don't give it to you by default because most people don't want it by default or care about it by default. But as a Mathematica user, you might. Okay. So what does it mean that the elementary charge is exactly this many coulombs? Well, of course, in Mathematica, that's not an exact number. When we see a decimal, we assume you have what kind of a number? It's a machine number. So what this statement actually means in Mathematica is I take this decimal number and I move the decimal over 9 places, so it's a rational number. So all these rational numbers with very large numerators and denominators start popping up. And most of the world doesn't care because all they care about is, well, it's approximately equal to this, to that many digits. But we do things exactly, so we care. And as I said, this also has implications. So Josephson constant is another constant that can be defined in terms of the elementary charge and the Planck constant. And so by taking these other constants and putting them together with a 2e over h, you find out it has that value.
It's kind of astounding.
And it doesn't really matter except when it does. It matters on a sort of higher level metrology framework. It's the right way to go. It has some very strange side effects, but it's actually beautiful. Yes?
Like on a philosophical level.
Yes. It's theoretical metrology put into practice.
Now, for the Josephson,
Yes?
it's the same goes for the von Klitzing constant.
Yes, exactly so. Okay, so here are now, as physical constant entities, the new ones that are new and old that are exact, and there's their symbols and there's their values. So, but we haven't gotten to the units part yet, have we? So what we really want to do is now solve for units. We know that Planck's constant is such and such joule seconds. We know all these other ones, so let's find out how the second is defined. Okay, so we can do that by defining a little bit of code, and here are the defining equations that we want to solve. Okay, so I've just basically, speed of light has meters and seconds plus this number, and all those other numbers I talked about are here too. Okay, so let's set up the equations and let's solve them. So there is the new definitions, some of which are not new because the speed of light was already there, but so the ampere is now some huge rational number times 2 physical constants, the elementary charge and the cesium hyperfine splitting frequency. And the kilogram one is really horrendous. I mean, the kilogram one is almost going off the screen and depends on 3 of the constants. And some of them get even worse, of course. So maybe this looks a little less intimidating if you factor them, but it's still pretty intimidating. And if you want to see how bad it gets, so let's just take our old friend, the joule. That should be, I think, kilograms meter squared per second squared. It just gets worse and worse. Tesla is, I haven't made a systematic search to find one that involves all 7, but there must be one. So with a little more effort, I could. But Tesla is already pretty bad. Okay, so there's Tesla. It involves, can't necessarily see it. Let me scroll it up for you. So these are all consequences of what was done in May of 2019. I'm perhaps running a little short of time, but I'll go over this real quickly, which is, so something as fundamental as the electron mass, we like to think of it just as a mass, but it can also be expressed in terms of other physical constants. And the most commonly known and useful one, involves the fine structure constant, the Planck constant, the Rydberg constant, and the speed of light. That's the first expression up here. And it just so happens that the physical constant entity domain knows about several of these equivalent forms because we knew they were going to be useful, so we started adding them. So what that is telling you is that if I take that first identity for the electron mass, it's equal to this combination of constants. Let me pull out the constants from that, and let me find their relative uncertainties for each of those 4 constants. Okay, so Planck constant and speed of light are exact. They have 0 relative uncertainty. Here's the 2, the fine structure and the Rydberg that I mentioned, that have finite uncertainty now. But what this means is that I can express the uncertainty of the mass of the electron just by normal error propagation by taking 2 times the relative uncertainty of the fine structure constant and adding it to the Rydberg constant. So there used to be, in the old CODATA, all these complicated cross correlations, and one measurement was correlated with others. The error propagation has actually gotten much easier as well. So this is really yet another simplification. So here's just a little summary table. There's a value in terms of fundamental constant. There's an old relative uncertainty. There's a new relative uncertainty. And there's the cause of that uncertainty. So here you can see there's a case where the magnetic constant, the electric constant, and the vacuum impedance used to be exact. They're now uncertain. All these others used to be uncertain. They're now so you're kind of pushing the problem from one place to another place, which I wasn't expecting when it first came out. So in summary, this redefinition actually, in principle, affects the unit system used by almost everyone. They're structurally important in eliminating dependence on sort of artificial human objects. So they provide a consistency and a universality that makes the system usable and stable probably from henceforth. Most people, almost all people, didn't notice this change, but because the Wolfram language does things symbolically, if you use units or constants in Mathematica, you will be among the select few who have the potential to actually notice it. I hope I've convinced you that this change, while the goal is to have it not look any different, was actually a lot of work to make not look different but still be correct in the Wolfram language. So this was about a month of work to back propagate this all through. The good news being now that it's done, it's pretty much done for all time. And those updates were done within a month of the redefinition, and they were made available. If you're using 12, they were automatically pushed to you via the Packlet mechanism, the Packlet update mechanism. So you don't have to do anything. You just started getting them if you use SI units. And I think I'm out of time, and I know I went through kind of a lot kind of fast, but I hope I at least gave you some overview of what happened, if or why you should care, and that confidence that whatever it was, Wolfram language and Wolfram alpha get it correctly. Thank you very much.